Thanks everyone for listening and for being here this afternoon. My name is Fidelis, and I'm a lecturer at the University of Western Sydney. So today I just thought that I will talk a little bit about some of the considerations which we have to take into account when we design civil engineering structures. So in this talk, I will try to maybe start from the beginning and talk about what we do as civil engineers in general, and then we can also look at the civil engineering structures of international significance, and also some of the design philosophies that we use for designing civil engineering structures. We'll look at strength of members in structural systems, and we look at how these members are loaded, and then depending on the loads which we have on the structure, we look at the design loads, and maybe following that we can have some general conclusions on the discussion. So if we think of civil engineers, what are some of the things that you guys think civil engineers do in general?
They can't respond.
Oh, they can't respond. So some of the things which we can do as civil engineers is to do structural design. So design of structures. We can also design foundations, which can be referred to as geotechnical engineering. We can also design and build water engineering systems and infrastructure. And in general, civil engineers are also supposed to have an understanding of environmental engineering as well. So among all these things which we are able to do, today we are focusing on structural engineering design, but with a main application to civil engineering. So one of the things that I thought I would do is to have a look at some of the most recognized buildings in the world. It might also happen that maybe some of the structures that I choose might not be recognized by some of us, because there are so many buildings around the world which everyone would sort of recognize, but I try to pick up some of the buildings that I think are of significance or might be recognized by others. And I also try to look at some of the world's most recognized bridges in brief. And then maybe as a homework for all of us, we can also try to look at some of the largest dams around the world. So although dams are water engineering structures, they also involve a lot of civil engineering structural design as well. So one of the buildings that I thought I would look at is the Q1 building in the Gold Coast, which is a high-rise building, maybe constructed between 2002 and 2005. It has a height of around 322.5 meters. And in terms of the material that we use, so one of the things with civil engineering structures is that we can use quite a number of materials. But if you look at some of the ones the materials which we normally use, so we tend to use concrete, we also tend to use steel, and sometimes we use timber. But for high-rise building in general, we normally use maybe concrete and steel, or maybe a combination of both. So we also tend to use composite structures. So for Q1, you can see that a lot of concrete has been used because it's a concrete structure, and then we have a lot of reinforcing steel. But at the top of this building, there's a spire which is made of structural steel, and that spire weighs around 250 tons. So the other structure which I thought might be of interest, or which people might have heard about, is Taipei 101, which was constructed between 1999 and 2005. It has 101 floors, and it's made from steel and also from concrete filled columns. So one of the things that you can see here is that with the concrete filled columns, so we can classify those members as composite members. So we have a tube which is made from steel, and then inside these tubes we have concrete infill. So one of the advantages of that is that because we have steel, which is a ductile material, and we have concrete, which is not a very ductile material. So when we have concrete confined in steel, it means that we are able to use a material which has high compressive strength, but then we also improve the ductility of that concrete because it's working in composite, or as a composite material confined by the steel tubes. So this structure, Taipei 101, is about 508 meters tall, and I think you can probably see at the corner here, we also have a steel pendulum, which is used for offsetting movement due to strong winds. So it's one of the features of the tower. Maybe as tourists from time to time, if you are able to go to Taiwan, you can have a chance to actually look at the pendulum, which is on top of the building. And maybe a building for the future, the Kingdom Tower, which is supposed to have started construction last year and is scheduled to finish in 2019. So this building is going to be 1,000 meters tall, and you can see from the structure that maybe the rest of this structure is actually a spire at the top. So a lot of times, I think developers of structures, they want to break records, and one of the ways they do that is to use structural steel to form a spire at the top, so that they can gain a lot of weight. The advantage for steel is that it's lightweight, and because it's lightweight, it's able to span very large spans. So if you take the spire as a cantilever beam at the top, so it's able to resist the wind loads which might be at the top of the structure, but still be able to be serviceable. So it's not going to deflect as much, and it's also not going to bend as much, and so it's able to carry the loads which are mainly wind loads at the top of the structure. I think a lot of times we don't consider timber to be a material that we can use for high-rise buildings. But as you can see here, there have been quite a lot of developments in timber structures. So there is a new type of material which is called cross-laminated timber. This material is manufactured using laminations of different layers. So by doing that, we actually improve the reliability of the material. And then if we use these panels, then they actually have compressive strength, which is quite close to that of concrete. But the advantage of timber as well is that it's not as brittle as concrete, and we also don't need to reinforce it as we would require to do for concrete. So this Forte building in Melbourne, it's 32 meters high, which is, I think, one of the tallest timber structures in Australia. But I understand that there are a lot of other buildings around the world as well, which are made from timber for sustainability reasons, because timber can become a carbon sink. So there is quite a lot of interest by engineers and developers in building high-rise timber structures. The other thing as well is that the construction process for these buildings it's quite fast. So compared to concrete and steel, the timber panels, so the cross-laminated timber panels, they are quite very light, and because they are light, so in terms of crane usage, we can use smaller cranes, and because the connections are quite easy as well, because we are joining timber panels with other timber panels using mostly brackets made out of steel. So they putting up these modules is actually very, very, very quick. And for bridges, I think we all know the Sydney Harbour Bridge, which was built maybe starting from 1924 and officially opened in 1932. I think one of the interesting statistics is, as you can see here, is that there were 6 million hand-driven rivets which were used. So if you look at that in compared to modern day construction, so we no longer use rivets anymore, so we use high strength bolts, and a lot of times we because welding processes are becoming more and more reliable, so we also use quite a lot of welding. So this is maybe one of those things which you can see that as time goes on, as we develop new ways of doing things and new materials, we also tend not to use some of the methods which we used to use in the past. But for Sydney Harbour Bridge, I think most of these rivets are quite sound, and the bridge is doing quite well for a bridge of that age. And the other bridge that I thought could be a bridge of note is the Milao Viaduct, which has a length of 2,460 meters. And at the highest point, if you are looking at the height from the ground, it has a height of 343 meters. And one of the tallest pier, I think it's Pier 2, it has a height of 245 meters. And you can also see that a lot of concrete has been used in this bridge. but the bridge deck itself, it's actually made from steel. So 36,000 tons of steel has been used to build the bridge. And now I think I can move maybe to talk a little bit about the design philosophy for structures in general. So one of the things that we try to achieve when we design a bridge is to make sure that the size of members that we have are actually able to carry the loads. So the sizes of our members should be able to carry the loads. And by carrying the loads, we mean that so if we have a bending moment, so the cross section should be able to carry that. If we have shear force or axial force, the members should be able to carry that. And we also have to look at combinations of loads as well. So when a structure is built, we know that it also has to support itself, so we have to look at the self weight of the structure, and it also has to resist other external loads. So when a lot of people move into a building, or maybe a lot of cars cross a bridge, we have to make sure that the structure is still able to support all those loads. So for steel structures, we tend to for relatively smaller structures, we tend to use open sections, such as the ones which you can see here. So we have these I sections, or some people call them H, and we have the C sections, and then we also have the these angles, which we normally use quite a lot in construction of smaller structures. But when we start to have large spanning structures, we tend to build what might be referred to as compound sections. So if you see this cross section here, it will be built from scratch, from plates, and it's going to be built maybe using a lot of welding, and also maybe some bolting as well. But the cross section of these members would be built to suit the span that we will have. So for instance, in this case, we have maybe the deck which is going to be spanning from this pier to this pier, and depending on the distance of that, so we need to have cross sections which are able to carry that that particular load. So we can so this is looking at steel, and then we can also look at concrete. So a simple concrete beam would have reinforcing steel and stirrups, and then we have concrete poured around this steel using formwork. So this is a simple beam, but if we also start to have quite large spans, such as the ones which you can see here, maybe from this pier to here, then we start to need to have special type of sections, and this is a box girder, as you can see, and so using these box girders, which might be maybe 2 meters high, and probably maybe 1.5 meters width, then we should be able to build a structure which is able to span a much larger distance compared to our normal beams or concrete beams. And in addition to that, we can also have pre-stressing. So we can have pre-stressing cables running throughout the section, because we know that concrete works mostly in compression. So when we use pre-stressing, we are making sure that concrete remains mostly in compression, and then it's going to be able to carry the loads that we require it to carry. And if we look at timber structures, so we already talked about cross-laminated timber panels when we were looking at the Forte building in Melbourne. But in general, for housing, we normally use sawn timber. So this timber could be softwood or maybe hardwood. But this is for useful maybe for domestic buildings, as I said, where we have much smaller spans. But as we start to build maybe structures which are made from timber with very large spans, then we need to start using special type of timber sections. So these are manufactured wood products. This one is a glow laminated timber, and you can see if you compare the size of the depth of this beam to this gentleman here in the picture, you can see that the depth of this is quite high. So through the use of much deeper beams, we know that we are going to be able to span much larger distances without any problems in carrying the loads. So this might be maybe useful for Olympic-sized swimming pools, for example, or maybe auditoriums in terms of construction. And one of the other things that we have to look at in terms of design is to make sure that our structures are stable and also they are serviceable. So by stable, we mean that maybe if a structure is built, it's not going to topple as maybe wind blows, or if we have an earthquake. So we have to make sure that our structures are fit for purpose. So depending on where the structure is, depending on the expected wind loads, and also depending on the expected sizes of earthquake, then we have to make sure that our structures should be able to support that external load and remain stable for us to live in them safely. Structures are also supposed to be serviceable, which means that over time, as the structure is in use, it's not going to deteriorate to a level where it can suddenly collapse. So maybe some of you might remember the I-35 bridge over the Mississippi River in Minnesota, which collapsed, and there are quite a number of theories as to why that might have happened. So I think some of the people think maybe there were some plates within the structure which were smaller than they were meant to be, but this is, I think, the difficulty sometimes of forensic engineering after collapse of buildings. It can be quite difficult to actually pinpoint what the causes of failures might be, because the structure anyway has failed. So you have, when you look at the structure itself, any point between the two banks, for example, could have been a member maybe which failed first. So we can sometimes it can be quite difficult to tell where the failure originated from. And for as part of our design steps, normally we need to look at the loads. So we need to determine the worst combinations of loads. We need to look at temperature effects, and sometimes some of our structure are just affected by the materials that we use within these structures. So if we use concrete, we know that we are going to have shrinkage. So when we have shrinkage, we might also have stress related to the size of members getting shorter or slightly shorter than we expected. And so the temperature effects could be an opposite effect. So what happens if we have a steel structure and we have high temperatures? I think some of you might have heard about the wheel in Melbourne, which was built, but because of a lot of warping within the structure, they couldn't use the wheel. And we also need to consider for welded structures, to consider the weld shrinkage. So when we weld structures, we actually induce stresses, which are referred to as residual stresses within the structure. So this is one of the considerations we have to have. And so if we are able to determine the worst combination of loads, then hopefully we should be able to use our analysis methods to determine the design action effects. So the design action effects are the design bending moments, the shear forces, and axial forces, and maybe even torsion. But we also need to look at, for some of these members, for a combination of all these. So we can have a maybe bending moment acting at the same time as axial force, and at the same time we also need to look at what the effect of the shear forces are going to be. So in looking at design, so we need to determine what the worst combination of loads are, and we also need to look at the resistance of the structure against the applied loads. So if we have the design resistance larger than the design action effects, then we know that the structure should be okay to withstand the loads which are applied to it. And I thought maybe we can have a brief look at how we design steel structures, for example, under bending. So for bending, if you look at this equation, so you can see that the nominal section capacity is equal to Fy, which is the yield stress, multiplied by the effective section modulus. So this is just to try to show you maybe the importance of knowing the material within the structure. So Fy is the yield stress, and I will talk about that a little bit later on. And if we look at concrete structures, so if we are looking at singly reinforced beams, then the equation for determining the moment capacity for these beams is given by this equation. And within this equation as well, you can see that we have Fsy, which is the yield stress of steel reinforcement, and we also have Fc dash, which is the characteristic compressive strength, and we have the width of the section, and also the depth of the section included. So this also shows us the importance of understanding the stress strain curves. So by using testing the materials that we are using and understanding their behavior, we should be able to use those values in the design of the structure. This is just to show you maybe one of the methods that we use for determining strength. So in this diagram here, you can see the cross section, and you can see the neutral axis. And for reinforced concrete, so we know that concrete doesn't do very well under tension. So what this does then is to ignore the concrete which is below the neutral axis, and then we are just using the tension from steel. So because the cross-section is in equilibrium, then we know that the compressive force from the concrete in compression should be equal to the tensile force in the reinforcing steel. So there has to be a balance, and if we wanted to know what the capacity of this is, then we can just multiply the either the compression or tension force by the distance between these forces, and that actually allows us to have a good idea of the capacity of this particular cross section. And so that's the equation which you saw earlier on. It's just formulated using equilibrium and also considering the forces under compression and tension in this case. And for briefly, if we were designing timber, then we also need to know the value of FB dash, which is the characteristic bending strength of timber, and we also need to know Z, which is the section modulus. But you can see here that for timber we have all these other factors which take into account the design conditions under which the timber is working. So for timber, we tend to, it's affected by moisture, for example. It's also affected by creep, so long-term deformation. And so we need to have quite a number of factors to take that into account to make sure that the capacity we determine is a safe one. So one of the things that we saw in all this determination of resistance is that we need to know the stress strain curves, and if we know what the stress strain curve is for the steel, for concrete, and also for timber, then we should be able to use those characteristic strengths in our design equation. So for us to do that, I think you might all be familiar with the determination of material behavior. So using for steel, mostly using steel tensile coupon tests, but we can also test steel in compression. And for concrete, normally we are required to know what the compressive strength is, but we can also determine the strength of concrete in tension, although we know that for design we normally ignore the strength in tension because it's very small. And this just shows the stress strain curves for steel. So if we have mild steels, they tend to have a yield plateau, which is considered to be good because when we have a structure under load, we want to have this plateau here to inform us when we have overloaded the structure. So when the structure is deforming at this level, we are given a chance to move out of the building, for example. So if you want it, say, it's good for safety of structures. But as the strength of steel becomes higher, or if we have cold formed steel, then we can have a slight differentiation in terms of the stress strain curve. So you can see that for grade 400 in this, we don't have a well-defined plateau as we had for grade 250 and grade 350, which are mild steels or low strength steels. And for concrete, we also for concrete under compression. So if we look at the stress strain curves, we can see the behavior of low strength concrete compared to relatively higher strength concrete, it's a little bit different. So for high strength concrete, we start to have more brittle behavior compared to lower strength steels. And so as I said before, the design action effects, what we need to consider is the different loads that we can have on the structure. So we have permanent load, imposed load, and we can look at wind loading, snow loading, depending on where the structure is, and we can also need to determine the earthquake loads. And in addition to that, maybe if you were looking at water retaining structures, then you are also looking at water pressure on structures. So the loads would normally depend on the location. So the wind loads depend on the location, the snow load on the location, and earthquake load on the location, and the use of the structure. So the live loads would depend on what the structure is used for. And this is just an example to show us how we can determine the design action effects. So by so if we have the loads on the structure, we should be able to determine the support reactions, and we should be able to determine the shear and moment functions. And by doing that, we should be able to draw the shear force diagram and also the bending moment diagrams. And just to conclude, so maybe in this discussion we can see that material stress strain curves are quite important. So either in tension or in compression, depending on the type of use that we have for the structure. So the stress strain curves are quite important for the determination of the capacity of members. So this is the resistance of members that we need to know. And in terms of design action effects, so the determination of bending moments, shear forces, and axial forces are also important because they inform us about the design action effects. So if you want the negative effects on the structure, so if we know these two things, then hopefully we should be able to design reliable structures for whatever design life we require. For the materials that we can use, we said we can use steel, concrete, or timber, but in most of the buildings, the materials actually work as a composite. So when we use steel, we also tend to use concrete at the same time. So then if we bond the steel and the concrete together using shear connectors, then we have what's referred to as a composite section. And in one of the buildings that I showed before, we also had tubular members. So if you have a tube which is filled with concrete, then it can also become a composite section. So maybe in addition to steel and timber, we also tend to use concrete and maybe composite sections. Oh yes, so one of the reasons that we tend to have maybe much more grand structures is because there is always development in the materials that we use. So I think you might remember these stress strain curves. So if we are looking at steel that is normally available, we tend to get mild and medium strength steel, and then maybe grade 400 is considered to be high strength. But now in around the world, there are other steels which have strength which is up to maybe 3 times more than 350. So we have some of the steels, even in Australia, which have a yield stress which is maybe around here, if you are considering this graph. So with a yield strength of around 1,350 megapascals. And if you look at concrete as well, now there are quite a lot of high strength concretes which have being developed. And those some of these concretes are also very high strength, so much higher than the 50 that I have here. So we have a possibility of having concrete strength very easily, which can be around 100 megapascals, so which is twice this strength. And I think in terms of concrete as well, now there are a lot of concretes that are available which are able to set very quickly, and you're able to reach a strength which is quite high because in the past we used to be able to achieve the full strength of concrete in 28 days, and now some of the concrete which is available is able to reach full strength in less than 7 days. So that also allows people to be able to remove formwork very quickly. So instead of pouring a slab and waiting for 28 days, you can pour concrete now, maybe where you can wait for 10 days, and you can remove the formwork and go to the next level. So maybe for timber, the cross-laminated timber that I showed you earlier on. So these are some of the ways we are able to put together timber in order to be able to make sure that it's very reliable, and we're actually able to build, in these cases, high-rise buildings using timber which is normally just reserved for domestic buildings. For myself, I used to work at Monash University a few years ago, and some of the work that we were doing at Monash involves the looking at equipment which is used in the mining industry. I don't know if you guys have heard of drag line structures. They are big cranes which are used in mining for digging and moving dirt. They can carry a weight of around, I think from memory, maybe more than 1,000 tons in one bucket. So that was quite an exciting project for me, because we had the responsibility of making sure that this structure remained reliable for use by the owner. Thanks very much, everyone, for listening.